Professor Leighton, the stage is yours.
Thank you very much. It's really a pleasure to be here today, and even a greater pleasure to be talking about Danny and some of his early work in technology. And I'll start with some of the technical contributions he made, and then talk about the creation of Akamai. And my goal is partly to celebrate Danny and his legacy. Also, I think Danny's a great role model for us all, but especially, I think, for students here at the Technion, where Danny graduated before coming to MIT. And then talk a little bit about the challenges we're facing on the internet, and some of the work that we'll now be doing here in Israel, Akamai will be doing in Israel. I'm going to start with a technical problem that motivated Danny when he came to MIT in 1996. It's really a classic problem in computer science of load balancing. Comes up all over the place. If you go back to the classic textbooks in computer science, Knuth, for example, he dedicates most of a volume to the problem of hashing. The problem you have is you've got a bunch of files, a bunch of items, and you want to put them into boxes or file drawers or computers or servers. And say you have the M items, and say they have names, call them X1, X2, up to XM, and you've got N servers. The problem is, where do you store each item at a high level? Now, there's some things you're trying to accomplish in this. First, you want to make an optimal use of your memory. You don't want to put all the items just in the first server, because then you're not using the others. You sort of want to balance out where the items go. Next, the items are going to get accessed, and some will be accessed more than others. A popular item, maybe the Google banner or something like that, will be accessed more than an unpopular item, your grandma's Facebook picture, say. And so you'd like to have the request load be balanced across the servers, in addition to the memory use be balanced. So you have access load and memory use being balanced. And of course, it has to be easy to go figure out which server you put it in, because a request comes for the item. You don't want to spend a long time figuring out which server has it. You need to be able to recall that really quickly. Now, the classic approach to this is using hashing, and the classic hashing algorithm that, I don't know if every student still learns this algorithm today, but probably they do, you can tell me, is you start by picking a random number. This is going to be a randomized algorithm. Call that random number A. And then the decision process is to put the item with name xi in the server you get, the numbered server you get, by multiplying that random number A times the name, viewed as a number, and then take it modulo n, the number of servers. So I'll give you an example. Say that we have n is 4 servers. The random number was 9. I mean, usually it's going to be a much bigger number. And the name of the first item is 7. Well, what we do is we take the random number 9 times the name 7, that's 63. Take it mod the number of servers, that's 3. So it goes into server 3. This is probably the most classic algorithm for assignment in computer science, certainly very basic. And the reason it's so fundamental is that it satisfies all these properties. Because of the randomness of the number A, it tends to spread the items out, even if they're different sizes, and balance out the use of memory. It tends, for the same reason, to balance out the request load for the items across the servers. And it's sure as heck easy to find where the item is. You just look at the name of the item, multiply by 9 in this case, and take it mod 4. Okay. It works great in a static environment where there are 4 servers today, tomorrow, and evermore, and it doesn't change. But if a server dies, or a server is added, or it's a dynamic environment, the algorithm doesn't work so well because the locations of the items change. And that's a bad thing. For example, say server 1 fails. Now you've got 3 servers, and you might logically rename them, 0, 1, and 2. And now you do your computation mod 3 instead of mod 4, and 63 mod 3 is 0, so it goes to server 0. Now, in the old days, what used to happen is systems grew. You would grow them by a factor of 2. And you would start utilizing half your memory, and you'd get all the way up to you utilizing most of the memory. And all of a sudden, you got to build out more capacity. You would double it, and you'd go through a painful day where everything would move around to a new location, because there was no graceful way of adding in servers. And if servers failed, you had a bigger problem. Now, this was a problem that occurred at MIT as we were thinking back in the mid-90s about, well, how would you use the web to store the cache objects? Because the web is not a reliable environment. The number of servers is changing. They get disconnected. You're growing consistently. You can't afford to move things around. And Danny came up with a beautiful approach to make hashing work in a dynamically changing environment. Now, the idea at a high level is very, very elegant. You take your traditional hashing algorithm, whatever one you used, for example, the one I described, and you map each file and each server to the unit circle at random. So in this case, we're going to put the servers randomly on the unit circle. We're going to put the files, in this case I think there's 8 files, also randomly on the unit circle using the traditional hashing algorithm. And the server assignment is going to be to just put each item into the first server it would see going clockwise around the circle. So these 3 items going clockwise go to server 1, x5 will get mapped to server 3, x1, x8 get mapped to server 2, and x3 and x6 get mapped to server 4. All right, so pretty simple algorithm. Now the nice thing is this produces a random mapping too, right? Because the server you get assigned to was randomly put there for next in sequence. So it has all the nice properties that the traditional solution had. It balances the use of memory. It balances the request loads among the servers with high probability. And it's easy to find the item. You know, you can make data structures that do this very quickly. Now the really nice thing is that the impact of removing a server is optimal, is as minimal as it could be. And let's see why that is. Say I killed server 3, and now I look at the impact of the mapping of where the items went. Well, the only change is that the items that were in server 3 now migrate to server 2. Nothing else moved around. And by the way, you say, well, that's bad because things doubled up or something. But in fact, if you look and do the math, if I had just not started with server 3, the others are just mapped randomly, they'd all have the same random properties as if you only started with 3 servers and the points were there. So the mathematics that says this thing load balances work the same when a server dies. All right, and because the servers are mapped randomly, when the servers 1, 2, and 3 fail, they're not likely to be together. They'll be spread out. So the mathematics works out very nicely. Same thing about adding a server. Say I add server 5, goes to a random place. What items change their location? Well, it's only going to be this guy that now encounters server 5 before going to server 1. So again, the only things that change are the things going to the new server that you added. And as you add a new server every day, the math says it all stays load balanced and very nice, very elegant. Okay, and so that's optimal because nothing else moved around, which is perfect in a dynamically changing environment. So this is very useful in dynamic environments, and today is widely used, not just by Akamai, but in all sorts of contexts on the web. Now, in fact, the details and how we really implement it at Akamai and it's implemented elsewhere are more complicated. In fact, because maybe an item is so popular it won't just fit in one server because that server can't handle the request load for that really popular item. In fact, sometimes items have to be in many servers. And so there's more complicated ways of doing this, and I can send the slides here with the archived history of this, starting with a paper that really had the early beginnings of the research that led to Akamai that appeared in a theoretical computer science conference There's sort of a funny story, as often is the case with papers that turned out to be fundamental, at least from our perspective in our company. When we first submitted this paper, we submitted it to the Symposium on Discrete Algorithms. Those of you who do algorithms research will know of that conference. It's a cross between theory and practice. And the paper was rejected because they said it had no hope of ever being of any use in practice. And of course, it did end up being pretty important, at least to us in practice. And then Danny wrote a thesis on this at MIT. It was an award-winning thesis. And then later, with another MIT student, we wrote a paper in Danny's memory that really went through and did a lot of the detailed work that Danny planned to do for his PhD thesis, but couldn't because he was killed. That does a lot more of the depth of the mathematics behind how you do these things. Okay, so that's sort of one of the real gems that Danny came up with. Now, when you think about, okay, how do you take that and now the problems we are thinking about as to how do you make the web work better? Well, first you start with, if you're building a website, you have web servers and you need the load balancing. And this is a critical algorithm, consistent hashing we still use today on load balancing. Then the guy who's building the website has to have application servers. And then, bad guys started coming, so you've got to have authentication servers and use SSL to protect your transactions. Then you got to make the site sexy. You got to have video streaming infrastructure to manage your web presence. Today, you have all sorts of third-party content on your site. It's not uncommon to have more than half your site be somebody else's applications. And then you have servers whose job is to offload all the other servers you've already bought, the app servers, the streaming servers, and so forth, to optimize your prior investment. Then bad guys started getting really bad, and you need intrusion detection systems and intrusion prevention systems and firewalls. We're going to talk a lot about that. The protocols are changing very slowly. DNSSEC has actually been around now for 20 years. We offer it as a service today. Very few customers buy it. IPv6, that's probably going to take another 10 years to convert from v4 to v6 fully. But the v4 space is running out. The top level registries are out. Regional registries will be out within the next year. And the gray market for buying v4 space is now getting very active. But converting to v6 is a painful effort. Now you have mobile apps and all the infrastructure needed for that. And of course, once you've done all that, it's not good enough just to have it in your data center. You've got to have your data centers be replicated around the world so that you can't be brought down just with one single data center failover. So the job of managing your web presence has gotten very complicated and expensive. And this doesn't even talk about the internet. Now the internet, I think, is the invention of our generation. It's really impressive how it's changing our lives, changing work, changing industry, changing government. At the high level, it's very simple. You click on the URL and your app shows up on the screen, like TV. In fact, the end users expect it to work like TV. Under the covers, it's not so simple. The internet is over 12,000 networks, and they're connected by peering points. And often, when you get your content from a data center or a cloud data center, it's coming from far away. And you'll go across long distances and through multiple networks to get that content, and that can make it be slow and unreliable. The data centers themselves become a critical point of failure and a great target for the hackers. They know where to go to corrupt your site or to bring it down. And the peering points are less understood, but a place where there's a lot of congestion and bad things happen. Famous examples when Level 3 got into a fight with a couple dozen other networks about who was paying who how much, and so Level 3 just disconnected them. And that meant for a period of a few days, people connecting to the internet through these networks could not reach content hosted by Level 3, unless they were Akamai customers, which we'll talk about in a minute. Now, the thesis behind Akamai, which originally was not meant to be a company, but was just a research project at MIT, was to take all that functionality that you put in your data center, put it into an Akamai server, and then spread the Akamai servers everywhere, literally everywhere, where there's end users. And the idea that in theory, back in the early MIT days was there's n of them, where n's a very big number and we're doing asymptotic analysis on it. And so the bigger that n got, the better off we were. In practice, we want to be close to all the end users in their city, in their network, in the last mile network. And the idea then is that when the end user goes and gets the content, probably it's already cached on the server, or a lot of it is. And so it's retrieved locally, which makes it be really fast and reliable. If the data center's down, well, no problem, because we have a version of the site backed up in our infrastructure in our Akamai cloud, so we can still serve the site. And even if we need to get back to the data center, we've built our own virtual internet on top of the Akamai servers, treated as nodes or routers. And so we use our own routing protocols, our own communication protocols, and our own application layer protocols to make the internet work for us and for our customers the way it should work, but never will on its own. And so if there's a break in the internet, say between level 3 and Cogent, we'll just route it around another network through level 3 to get back to the origin where a database or critical database might live. Okay, so this was the theory idea, and I'm a theoretical computer scientist. I proved theorems for a living. That's what Danny wanted to do for a living. He wanted to be a professor at MIT or doing algorithms in theoretical computer science. I wrote very little code, and it was embarrassing when I did, and Danny wasn't interested in writing a lot of code. Very capable, but not his primary interest. But we were interested in using algorithms, at least in theory, to make the web work better. And this is sort of the timeline, and I'll go through this, as to how this theory project evolved into a company. And I have to say that at least I'm the most unlikely person in the world to start a real company. Just totally clueless. And Danny had no desire to start a company then. But one thing led to another. First, we looked at all the problems you'd need to solve. And I talked about load balancing and server assignment. There's a lot more. You got to make sure the content is always fresh and always accurate. You never want to serve somebody else's content on the wrong site. You just can imagine the horrors in doing that. You have dynamic content, and we need to be assembling that uniquely for the end user on a server near the end user. That presents a whole bunch of challenges. Everything has to be distributed. At scale, you cannot run centralized algorithms. So this is a great case study for distributed algorithms. It has to be secure, and we'll talk a bunch about that. When you do streaming and webcasting, there's no notion of caching. When you have to take a stream from a source like the Olympics and get it to everybody who wants to see it in real time. And this is a problem we didn't think about in the early days, but you have to be able to log everything you do, report on it, and bill on it. And it has to be right. And finally, operations. The network can never go down as you're changing software, which turned out to be a challenge that we discovered early on when we created the company. Okay, so we were doing research as theoretical academics, and literally one night, Danny was sharing a beer with his next-door neighbor, Pritish Nijawan. Pritish was in the Sloan School, that's MIT's business school, and Pritish's wife babysat Danny's kids. Now, Danny was crying in his beer about his impending personal bankruptcy because he had 2 kids in private school. Danny was a theoretician, a theoretical computer scientist, and back then that was a dirty word. It's before the days of Google, Akamai, Amazon, where now people who do that stuff are heavily recruited. But back then, he had no hope of making a lot of money, and his wife didn't work. And so literally he had huge loans building up, and he was contemplating bankruptcy. And Pritish said, wait a minute, you're doing this really cool research on the web. That's a pretty sexy thing, and there's this contest at MIT called the 50K contest, which they mistakenly thought meant that the winner of this contest, which was a business plan competition, would get $50,000, and that was perfect for Danny because that would cover his debt. And so he convinced Danny to, hey, let's get that thesis work turned into a business plan. We'll submit it. We'll win $50,000, and it's great. And they needed somebody with gray hair, and I had enough then. And Danny was my student. They talked me into joining the effort. The team was called Cache back then, not Akamai, because it was a play on caching, because we were caching web objects. And we won the software category of the first round of the 50K. And that's called the 1K, and there were 10 categories, so we got $100, and we spent that on more beer. And Pritish was all excited. He said, guys, this is big. Real companies come out of this. And Danny and I had no intention of forming a real company, but it was sort of cool learning about, writing a business plan. We got books out of the library, how to write a business plan. To show you how clueless I was, I didn't know what the acronym VC meant. And if you told me a VC was a venture capitalist, I would have said, that's very nice. What do they do? Just really clueless. Anyway, we went forward, had a little more beer, got jazzed by Pritish, and we made it to the final 6 in the competition. Now, urban legend has it that Akamai won. That's not true. They only announced first, second, and third. First place was a tie, actually, with a nonprofit. We were not first, second, or third, and in fact, after we saw the other presentations, I'm sure we'd have been ranked 6th if they'd have said, who finished last in the final 6. It was a great slap in the face. And these are people that, probably some of you, of course, here know Danny. Danny did not like to lose. Danny liked to win. And Danny had a lot of drive. And Danny was pissed, when we lost. But it really charged us up. We understood why we lost. We were lacking real, business talent. And it was a great, actually, experience for us. Now, afterward, after we lost, we were approached by some of the VCs who were the judges. And they came to us and they said, look, this is great. Let's form a company. It's MIT. It's the internet. It's sexy. We're going to start this company. In 6 or 12 months, we're going to flip it, and we're all going to go home wealthy and happy. And this is the final proof point for how naive we were. We said no. Because we weren't sure we had the right business plan yet, that it would really work. We had not written a line of code. We had theorems, and there's a big difference between theorems and code. I liked being a professor. Danny wanted to be a professor. So we said no. Danny went off to Bell Labs for the summer. It was a primo summer internship for him. And we said, well, we're going to keep thinking about it. I hired about a dozen undergraduates to do a coding project over the summer to build a prototype. And we stayed in touch. We worked on the business plan. And we thought, well, if we can get the business plan to work and we can get some code that actually demonstrates it, we'll reconsider at the end of the summer. Now, at that time, the business guys that had gravitated towards us when we were doing this went out and did form companies, multiple companies, to take the technology, some with our business plan from the competition. Some got a lot of money and funding. They all ultimately failed. Now, so we developed some very cool prototypes at MIT. We modified the business plan. And at the end of the summer, we got together. And we had tried to get ISPs to buy the technology or take the technology and use it without any success. They said, thank you very much. We've got more important problems. Everybody knows distributed computing is an ivory tower concept. It doesn't work in the real world. Please go back to your ivory tower. So we had no success there. But in the end, we decided the only way we could make this technology be useful would be to do it ourselves. It was a very tough decision because we had no business experience. But we thought we had a chance, which is a rare chance, being a theoretician, being somebody who does mathematics and algorithms, to have an impact. And so we said, okay, we're going to give it a shot and make it work. And of course, those of you know Danny, once he decides he's going to do it, there is nothing going to stop him. So we left MIT. We hired employees using friends and family money. It took us actually a while to close the first round. We got Paul Sagan, who was hired by one of the VCs to vet us, and we got him to be our president to join the team, and he had real business experience. We deployed some servers that we bought with our own money in Exodus data centers. The first live test of the system using content on a customer site was a tiny little pixel buried deep in Disney's site, www.disney.com. And I remember we were thinking about it today as we were driving up here, not far from the Golan Heights. Danny actually had to leave at this critical time for a mission here. So he was in the military, still active with his unit, I guess in reserve duty. And so he had to go back for a few weeks. And I remember he called up using some fancy radio. He couldn't say exactly where he was, but it was somewhere, at the edge. And while we were, turned on that first live object, and we were all hitting it, we were delivering that object maybe once every, a few times a minute, because we were clicking on it. Nobody else really could see the object. But it was sort of a special moment, and Danny was hooked in live through the military network to see it. Our first big break was March Madness. That's the college basketball tournament in the United States. We had tried to get the guys that hosted ESPN to try our service. Our strategy was to get the top 10 name brands in the business to try it. And we were having really no success, as you could imagine, until ESPN went down. And they called us up and they said, that test you were talking about, we'd like to try the test now. We said, great, here's how you turn on Akamai to Akamaize your content. And within 15 minutes, they were pumping 3,000 hits a second from one hit every few minutes, which was us. And they noticed that their site not only got back online, but was 5 times faster than it was before March Madness started. So it was a huge breakthrough for us because they were the best in the business back in '99. The other, coincidentally, big break we got was that very night, and this had been planned in advance. Back then, the Star Wars movies were big deals, and Entertainment Tonight approached us about distributing a trailer for the upcoming Star Wars movie. And we said, great, we can distribute the trailer. And back then, the trailers were a big thing online. Everybody would go download the trailer. Now, we didn't know it, but Entertainment Tonight had a bootleg copy of the trailer. Steve Jobs from Apple had procured the exclusive rights to distribute the trailer on Apple's site to get everybody to use QuickTime. And to make the idea, his hope was that QuickTime would become what Flash ultimately became. So it comes to Tuesday night at 9 o'clock, the same day we'd done March Madness, and the trailer's released. We get it, and we distribute it, and things are going great. And within a few seconds, Apple.com is down, and all the other bootleg sites are down. But we're distributing the trailer. And a guy at CNN, who's a techno guy, said, well, what's going on here? What's this Akamai thing? He digs into it and found out about Akamai, and then they wrote a story, broke the story that Apple's down, everybody else is down, and there's this Akamai thing distributing the Entertainment Tonight bootleg copy of the Star Wars trailer. Now, Steve noticed, and literally we got a call about a week later on April 1st, which I don't know if you have April Fool's Day here or not, but we have that there. Calls up Paul, says he wants to buy the company, and it's April 1st, So Paul goes, yeah, and then he comes out looking at Danny and me, all right, which one of you jokers is pretending to be Steve Jobs trying to buy the company? Wasn't us. Paul goes, oh, crap, and calls back up Steve. Now, we didn't sell the company, but we did take Apple as our first strategic investor. And to this day, they're our largest customer and a huge partner. So everything Apple does, to this day, they do with Akamai. All the iTunes, all their movies, everything, all their software. The iTunes store comes off Akamai. And we grew the company. We got a lot of buzz out of those two events. Everybody, in the industry at that point, in the bubble industry, knew about who Akamai was. It was great. So we grew like mad. Money was, falling off the trees. It's back in the bubble days. We went public, a year later on my birthday, from the date we founded the company. We were losing millions and millions of dollars. Had no revenue, and we got a $35 billion valuation. It was nuts. There's no explanation for it. It was one of the 5 largest IPOs ever. Totally insane. In fact, it's crazy. Their investment in Akamai they made was worth more than the rest of the company. on paper. We could have taken if they would have sold, which they wouldn't have, just a tiny dilution to buy Apple. It was just those wacky days. It's hard to imagine now. We bought a bunch of companies because that was the thing to do. We just grew like mad. We bought real estate everywhere, which we soon thereafter regretted. Hired lots of people, and then all hell broke loose. The worst, of course, and just a horrible tragedy, Danny was killed, on September 11th. It was just a disaster. We had to lay off 2/3 of the company. We were down to a couple months of runway in terms of cash. All our customers were going broke. We had to revamp the customer base. Huge pricing pressure all of a sudden. We had no budget. We didn't even have a real CFO. We had an analyst as our CFO because that was the thing to do to go public then. We had to get rid of all that real estate, which we could do because we said you can take $5 million in settlement now or see what the bankruptcy judge gives you later. And our market cap went from 35 billion to 75 million. And it happened so fast, we went from the problem of having teenagers that became zillionaires at the IPO. Some of them had taken their options and incurred the taxes but not sold the stock. And now they're literally owing tens of millions of dollars to the government with nothing. They were teenagers at MIT. Just total disaster for the company. And here again is, I think, where Danny's spirit of never give up, never say die, take any hill, just carried the company, even after his death, and living in his memory, drove the company and drives the company today. His legacy and spirit, truly still drives us. We got through that period. It was extremely difficult, but we've been growing and delivering on the vision ever since. Today we're a very successful company. We have over $1 billion in revenue now, substantial profits. We generate over $300 million in cash a year. Pretty decent market cap, and we're in most of the top lists of major companies. And we've finally grown beyond where we were in the wild bubble days. Today we have over 100,000 servers, and that's not the important number. I mean, Google probably has millions. The important number is those servers are in thousands of places. Google's in tens of places. And that difference is important. We're inside 1,000 networks. I'm not talking about peering. I'm talking about being inside their infrastructure in 650 cities in 74 countries. In fact, if you want later, I can show you a demonstration. We weren't able to hook it up here that shows you where they all are. It's a pretty cool interface for that. We deliver all the major websites today, pretty much. Certainly all top 60 commerce sites, all top 30 media and entertainment companies, 9 of the top 10 banks. We deliver a lot of traffic. Daily, it's almost always over 7 terabits a second. We've gone up close to 10. We do over 20 million deliveries per second. That's over 1.5 trillion deliveries every day. And a delivery is where a browser asks us for something, we deliver it and log it. It's a GET request that's satisfied. Just huge volumes. And we don't know the exact percent of the web we are, because we don't know what the base is, but it's a large fraction of the web today rides off this platform. You're not going to see it live, because we couldn't hook it up, and in fact, I'm probably running out of time. The reason people buy our services is that we make their websites be faster and more reliable, and make them be better, and that makes them do more business. We also save them money. So when they buy our services, net, they save money on infrastructure build-out, because we're cheaper than what they would spend themselves, and it makes their website be better, which means they make more money on their website, or make more use of their website. And we now have hundreds of case studies to prove this. Today we're focusing, I can talk a little bit about 2 major areas, mobile and security. And security is going to be a major area of our investment here in Israel for R&D. If you look at the top desktop sites as measured by performance, today 3 seconds is sort of an average. People are trying to get down to 2, the portals are trying to get down to 1 second. If you look at mobile, it's a mess. Those same top sites, 9 seconds. 9 seconds just doesn't cut it. That's like 2001 technology for the desktops. The expectation of users is that this device should be as good as this one. Why should it be much different? People expect it to load quickly. The reality is it doesn't, and this leads to disappointment and the lack of business on the mobile devices. So this is a problem that we've got to solve. It's a hard one. There are fundamental reasons why the mobile devices are not working so well. And that's because the wireless infrastructure was built for voice at about 8,000 kilobits a second, 8,000 kilobits a second, sorry, 8 kilobits a second. Whereas today you get that device and you're thinking you're going to these rich web pages or video, or you're going to watch the soccer game on your device, which could be hundreds of kilobits a second. So you can be growing by a factor of 100 on the traffic, and the infrastructure is not there. Now we're going to 4G, right? That'll give us one user can now get up to 100 megabits a second. Collectively, the bandwidth may be a factor of 10. We need to grow it by a factor of 100 or 1,000. Now, today we have a product that can make it be faster. We can't get it as fast as the landline yet, but we can make it be faster. And we have a really exciting partnership with Ericsson where we're going to be embedding the Akamai software and technology in down all the way to the tower to prioritize the bandwidth. So that the idea is we will sell a service to our customers that gives them an end-to-end quality of service guarantee so that their traffic is what gets prioritized at the tower. Now, today, the traffic that gets prioritized is the device that has the best signal to the tower. But they might be looking at a video that has no economic value in zillions of bits, as opposed to the eBay transaction that has a ton of value, real dollars, and virtually no bits. And the value per bit can vary by 10,000 to 1. And so we're going to be able to do the prioritization and sell a service that gives access to, to those who really can pay for it to the best performance. And that'll actually put more money in the ecosystem to share with the carriers so they can build out more. There's also some pretty exciting things we're working on here with Ericsson, because when you have the device, it has a SIM card that's cryptographically secure to identify the end user. And by working with the networks, because we're in the networks, we can take that information and now enable people to buy stuff on sites without identifying themselves or even entering their credit card, because we have that through the carrier. Right? Today, Amazon, of course, has your credit card. But most of the sites you go to don't, and you may be reluctant to use your credit card. And this will make e-commerce work a lot better for the rest of the sites beyond Amazon and eBay. Let me take a little bit about security. And now we were supposed to end at 12. We started late. Is it okay if I feel free to go if you got something else? I'll try to finish up quickly here. But this is particularly important because we're focusing on this now in Israel with our R&D and recruiting here. I could sum up the state of internet security very easily in one word. It's bad, and it's getting worse. The typical attacks that we see today have a volume of about 3 to 10 gigabits a second. And that's much bigger than any website, pretty much any website, not, Amazon maybe, can handle on their own. And they come from all over the place, and they move rapidly from the sources, which makes it very hard for websites to defend themselves against reasonable scale DOS attacks on their own. The big ones are enormous, hundreds of gigs a second. You can also see here the rate of the attacks that we're seeing in just our customer base. You go back to 2009, we had about a dozen major attacks against our customers. We thought that was a big deal until last year. Over 500 received major attacks. That's just a huge increase. Now, you can say, why is this just exploding in terms of the hacking going on? You have the traditional glory seekers, but that's not the big problem today. Political hacktivism is a huge issue today. Anonymous and groups like that. You have cyber crime, organized crime, cyber extortion against websites. Well, they'll bring the site down and say, if you want to get back online, deposit $50,000 in this account. And people pay. It's a big business coming out of Eastern Europe, Russia, and Asia. And state-sponsored attacks, where actual states are trying to either steal information, sensitive information, or prepare the way for a potential future devastating attack. I'll give you some examples that we've encountered. The Sun is Rupert Murdoch's largest tabloid in England, and they were an Akamai customer. They use us to deliver their site, but hackers got in and changed the front page on his newspaper with a story saying he died of a drug overdose, and they put a very unflattering picture of him on his own newspaper. Now, if you'd asked me a year ago, would I think this could happen, I would say technically yes, but the chances that, Fox, this would happen to, those guys, no. It happened. Now, we have security solutions that stop this attack. They had not bought those. That night, they bought them. The next day, the attackers came back and were trying to plant another story about Rupert that would have been unflattering, and it was blocked by Akamai. This is, we have lots of examples with cyber extortion, particularly during the holiday season. Here's an example of the traffic profile that happens. They come in and they slam your site with traffic levels that are thousands of times normal. So you can't possibly stay up on your own or afford to stay up when the traffic goes up by a factor of 1,000. But with Akamai's platform with huge capacity, that's no problem. We just deliver the attack traffic, and the site stays up, thereby avoiding the lost revenue of being down, which is substantial during the holiday season. I don't think I'll show you this video because we're low on time, but this is an example where Anonymous announced in a YouTube video an impending attack on Fox News, calling all the faithful to bring down Fox News sites. And they listed, the reasons why and who they were after. And they announced the attack for November 5th, last November, on the Guy Fawkes Day, who's sort of their mascot. And Fox News turned to Akamai, Akamized with the security services, all the news sites. And here's some of the reports that we saw in the chat rooms after that happened. So it comes to November 5th. The sites are now protected by Akamai. And these are the hackers, some of the posts made in the chat rooms by the anonymous hackers, saying they've found nothing. We might not be able to take it down unless some of the elite anonymous hackers join in. There's dozens more of these chats. I won't show you them all. It's a tough nut to crack. They were prepared. And then finally, this is the goal, because Anonymous is pretty serious. They've gotten some pretty good headlines from taking down sites. They're very good at it. But here you have one of the very elite guys saying he tried all night, couldn't do it. It's embarrassing because Anonymous had gone public 2 weeks ahead saying they were going to do it, and they weren't able to do it. And of course, what you want is for them to be able to back off. Now, the challenge we have as a company is that you have very serious adversaries out there, all the way to major nation states. And our job is to develop the capabilities to protect the leading enterprises and websites with our services, to keep them from being brought down, to keep their sites from being corrupted, and to keep their data from being stolen. Now, at a high, simple level, the way we do that is this is what a web application looks like without Akamai. You have your web server in a data center. Maybe you got a firewall. You poke a big hole in that firewall to let the world in, because you got to let the world in to access your website. The problem is the bad guys come in volume and with sophistication, and they bring you down. You can have the best firewall in the world, the best IPS, intrusion prevention, intrusion detection systems, and if they come in volume, you will go down in a data center. With Akamai, everything comes through us, and only Akamai goes back into the data center. And we have pretty sophisticated firewalls on our servers, and so when the bad guys come, they can bring down Akamai servers as I speak. They're bringing down hundreds, but we've got 100,000, and we automatically direct people to other locations. And so nobody knows the site's under attack but us and the owner of the site. Now, the exciting news for us and why I'm actually here today versus another day is that we've recently acquired Cotendo. And this is an office that now gives us a great presence. They have outstanding folks here in Israel. And it is our goal and plan to grow this office, already a great R&D center, into truly a world-class R&D center for Akamai. We are basing some of our key server technology development here, and we're basing our security service software development here, which are in the security services is the fastest growing area of our business today. So it's a very exciting development for us. And I'm here also in part, not only hopefully to inspire you in your own entrepreneurship activities and your own computer science research, but also to recruit. We are looking to hire the very best folks and to provide a very exciting opportunity. We're not Google. We're not like Google in the sense that Google, there's thousands and tens of thousands of developers and researchers, and you can work on whatever you want, and almost none of it will ever see the light of day. At Akamai, we're a smaller group, very high class, very strong in Danny's image, the very bright, hardworking folks. And what you develop will be used. That's just the way it is. And your code will go out there and everybody will be using it. Because everybody here is using Akamai software as you build things. So it is an interesting opportunity for people that are interested in that. We have Hila here. Where's Hila? You can talk to Hila for more information if you're interested. We were already talking about setting up a summer internship program this summer for folks here at the Technion. And we have an alumnus, David Dry. Where's David? He's an alumnus. You can talk to him also about his experience working in the office here. So let me end there. I'm sorry we ran over, but I'm happy to talk with folks.
Thank you very much. There will be some questions from the audience. Yes?
Mine just was a question. Is the analyst turned CFO Tim Weller?
Yeah, but don't tell him I said he wasn't a real CFO. But we did have an interesting experience with, what's a budget? That's right. Tim is a great guy. Love Tim.
Just for people to know, he got his PhD in WE at the University of Illinois. He's a very smart guy.
Yes.
Not some intern CFO.
Now
I know him, and I was wondering.
And he's a great guy, and I'm backpedaling quickly. But he wasn't the CFO before he joined Akamai. He was an analyst.
A more serious question. Is there a notion of false positive or negative whereby you deem something to be an attack and somehow block it even though there's legal legitimate accesses and you're blocking legit business?
Yes. And so we have a range of tools, and we let the customer decide, each customer decide where they set the alert and where they set the block. And it's at the IP level, depending on what they're doing. So an example might be that a particular IP address is causing a certain, like maybe 5 errors of a certain type at the origin per second. Or it's causing 20 exercises of this application back at the origin per second, as opposed to being served at the edge. And so they will set a threshold when they want to block. They also have the option to say, okay, before I let this guy in anymore, I want to pass a CAPTCHA test, check a whitelist, do something else that will try to diagnose, is it a bot or a real human? Because the last thing you ever want to do is deny real traffic. So there's a whole range of capabilities we have around that. Yeah.
First of all, thank you for a very interesting presentation. When I first heard about Akamai a few years ago, the description given was, let's say you're in Australia and you want to access something that's in Boston, instead of having to go through everything and underwater, etc., you could go to the Akamai server in Australia. And I assume that's true also for other rural areas, particularly places like Africa, which have a much more difficult infrastructure, etc. How do you at Akamai balance serving more out-of-the-way places, whether it's undeveloped places like Africa or undeveloped places like Australia, which might be just as far, with areas that are more profitable? Sort of how does that all work?
Well, we want to have our servers wherever the end users are. Now, usually that means most of the servers are in the bigger cities. But we are in a lot of remote locations. We will deploy servers for customers that have a branch office that's important, there. We also have our software now on a lot of client machines. In fact, we have 30 million clients, which I can show you those. We weren't able to hook it up, around the world. And so you can go see in Siberia, there are several thousand active clients that are assisting Akamai in delivering content from their machines. And so that gives us a really nice and easier way to get into the most remote locations in the world, to assist with the delivery of content. And we will, when stuff's cached, we'll deliver it locally. And when you have to get back to a data center for a particular critical database, we'll facilitate that communication and make it be faster. Yeah?
Can you comment on the rate of growth of the internet in terms of, I don't know, bandwidth storage that you have to keep servers and so on?
Yeah, so the traffic is driven by, I think, video today. Software is a big driver of traffic as well. As there's more devices, they all got to have software updates, and that's all over IP now. Video today is still about 1%, maybe 1 to 2% of watching video is done over the internet. That's going to explode. Our traffic growing a factor of maybe 3 per year there, 2 to 3 per year, depending on how you look at it. I think it's going to increase and get much larger. Today we're at 10 terabits a second. We're building out for 100 terabits a second in the near future, and we're probably going to go through a whole different architecture to go to 10 petabits a second. Which is where we see it going when you start watching, more people start watching high quality video more of the time online. So it's exploding. The devices, the connected devices are going through the roof. There's more devices connected today than there are people.
The static storage that you keep?
That's growing like mad because more and more movies are going online, which is what drives the static storage. So it's exploding. In fact, our traffic this year is growing almost twice the rate it was last year. Huge increases in volumes. We're at volumes that are hard to contemplate when you think about all the traffic that we're serving today. Yeah?
How do you handle dynamic sites? Do you run the code on your servers? And where do you save the data?
Yeah, the primary way and the simplest way is that for the dynamic part, we'll go back to the origin and get it, every time. And we use our own routing for that, our own communication protocols. We do things like prefetching and stuff to make it be really fast. So that even if we cached nothing, we'll make your experience with that app be 2 times as fast, 4 times as fast, depending on where you are and where the origin is. We do have the capability, and have had it for 10 years, it's like an EC2-like capability, where the app actually runs on our servers. We don't sell it in a way of swipe the credit card and you can buy some CPU. We don't do that. But for our big customers that want their apps to run on our platform, we do that. And we are supporting now, in certain cases, for certain customers, large VM, capabilities. For the very biggest customers that want to do big operations, you can think of it like an EC2, but we do it differently in the marketplace, and we don't advertise like you wouldn't use us as an individual for that.
You mentioned that other people, other VCs, try to implement the idea of space. Can you maybe comment on why Akamai actually succeeded and others didn't?
Well, in one word, we could say Danny, is why we succeeded. But really, it's Danny's the personality there. And it's the personality that still, I think, pervades the company. It is smart, hardworking, never give up. Technology matters. I remember one of the guys who was on our team in the 50K competition. He was actually a businessman from California. And he went to go form a competing company because we said we weren't going to start one then. And he said, it's execution that matters, not the technology. And that he was fine going off on his own because he knew how to execute and he didn't need the technology guys. We said, okay, you can do what you want. And there was, in the end, I think, execution matters, but so does technology. And so do the technical people. And I think it was the technology that the really smart technical people developed, that made the difference because all the others failed. Before we were through, there were dozens of them. They called them yaks, yet another Akamai killer, as they were created to come after Akamai's business. And Akamai today has still been very successful, and none of the other companies have. And so I think it is what Danny was about. Be really smart, really technology, really driven, never give up, and driven to succeed. Yeah.
For the mobile, are you able and allowed to use the physical multicast, wireless, and storage into, say, smartphones as sort of caches that help reduce the load, or is that?
That's a great question today. Multicast is not used today, but it's our view, and we are driving now through development to try to make that be a reality. Multicast has existed for decades now. It's used within some enterprises. It is not used on the internet. We believe that it can be, and because we're inside 1,000 networks, because the networks will do it differently, even one network won't support it all through the network, but where it can be supported, we're going to have our servers there trying to exploit it, not just in wireless, but also in the internet. And that's one of the ways that we're going to be able to make video distribution work better. And the goal is to work with partners that have devices in the home. Maybe it's your cable modem, maybe it's your movie media hub that'll have our software on board to take the multicast, to get the bits they didn't get, the packets they didn't get, to do client-assisted delivery. And that's where we're driving to. And I think that'll be the major architectural change that takes us from 100 terabits a second to 10 petabits a second. That'll play a critical role. So we're working very hard on that as we speak.
Okay, so I think we'll conclude now, and
Thanks very much.